Okay, good morning. This is Professor David J. Del Reyes. Okay, the date for this morning will be November 11th, 2023, and the time is, hey guys, it's morning, 4:18 a.m. Okay, my topic for this morning will be a continuation of my lecture on AC machines. Okay, AC machines, and we are now on lesson number 56. This is the so-called study of power generation, that is alternator. Okay, let's proceed. The subject matter for this morning will be AC machines, lesson number 56. And the title of the topic, it's a very interesting one because for this morning we will now be deriving the formula on how to compute the generated voltage of any alternator. So what we will be deriving will be a general equation. So the title of the topic will be the derivation of generated voltage of alternator or alternators. Okay, let's try to bring out the derivation. Actually, we are interested in the so-called formula and how to compute it is this one. Why there is a factor 4.44, okay? It's not a magic, it come from somewhere else. Okay, the start of the derivation will be from by using this equation here. I think this is from physics, you know. The generated voltage in any conductor will be the total number of turns times the rate of flux with respect to time times 10 to the minus 8. And this is actually volts. Like what I said before, the needed things to generate voltage is just a conductor and a magnetism. A conductor and magnetism, right? So the conductor and magnetism interacts, it will generate alternating current voltage. This is the first formula where we will start the so-called derivation. A is equal to N flux with respect to time times 10 to the minus 8 volts. I place it here when time t is equal to 1/4 of 1 over f. 1 over f is actually the total time. What is total time? It is here. The graph of the generated voltage for an alternator will be sinusoidal wave. Sinusoidal. It's a sine wave. At time t equal to 0, the voltage is 0. It goes maximum. It goes 0. It goes negative minimum. The only significance of this downward curve is that actually it alternates. It changes direction. Okay? Then it goes again to 0. That's a one complete cycle. And the total time involved from 0 to 2 pi is actually total time t. It's designated by capital letter T. And if we try to compute for the total time, it is actually 1 over frequency. And in here, I place it there. When time t is 1/4 of the total time, the instantaneous voltage is actually equivalent to E average. Okay, let's try to imagine that E is equal to E average when time t is equal to 1/4 f. It is something like this. The total time for one cycle is 1 over f. So this portion here should be 1/2 f. The other half portion will be 1/2 f, right? And according to that, we will take again 1/2 of this one. If we try 1/2 of 1/2 of 1 over f will be 1/4 of 1 over f. It's 1/4 of 1 over f. It says here when time t is equal to 1/4 of the total time, the instantaneous voltage is actually the average voltage generated by the generator. And where is that? It is at this location here. This is 1/4 F. Okay? So if I will try to bring out the 1/2 portion of the sinusoidal wave, it will be this one. Right? And according to that, at this location here, if we try to take the magnitude of the voltage here, it says E average. And the total time involved at that one is 1/4 of the total time. It is this. Okay? So don't ask me where I get this T is equal to 1/4 of 1 over F. It says E, the instantaneous voltage is equal to E average. It came from here. Okay? Actually, this is just like what they call this integral calculus. The area E average is actually a rectangular thing. So if we cut this one here, we transfer this portion here, this portion back here, right? We transfer the upper portion back here. So actually we could remove this one now. Okay? So what will come out is actually a rectangle. And the height of this is actually termed to as E average. Okay? We remove this half portion here, we transfer it here. So the resulting figure now will be something like this. So actually the total area covered by this one is actually E average. Okay? Oh, it's not magic. Okay, it came from here. I take 1/2 portion here. I remove this portion, I transfer it here. Then I say this rectangle here now represents E average, this height. Okay? So there's no problem here, right? So by using this equation and using this condition here, time t is equal to 1/4 of 1 over F, it says from that explanation, the instantaneous voltage is actually E average. So substituting this t here back here, E average now will be the total number of turns, open bracket, flux, total time involved is 1/4 of 1 over F, close bracket, times 10 to the minus 8. And if we try to simplify this one, we multiply this, total turns times flux, okay? We change the operation from division to multiplication. We will take the reciprocal of 1 over F. It should be 4F over 1, close bracket, times 10 to the minus 8. So the average voltage now will be a factor 4 times frequency times flux times the number of turns times 10 to the minus 8, and the unit of this will be volts. So the general equation on how to compute for the average voltage generated for any alternator will be factor 4 times the frequency times the flux times the total number of turns times 10 to the minus 8 volts. So actually the parameters that controls the average voltage generated by any alternator is the frequency, the flux. Flux is the magnetism. Okay, we needed the flux to generate voltage. And here is the total number of turns. That's why I told you before, to generate voltage, there should be flux and turns. And here, this now includes frequency. Right, in this formula. But the main thing here is there should be flux in total number of turns. Because if the flux is 0, we could not generate voltage. If there is flux and there is no number of turns, meaning there is no conductor, we could not generate voltage. So it's a must that there should be a flux and there should be a conductor that will interact with each other to generate an average voltage. So from now on, under the study of alternator, the average generated voltage will be 4 times frequency plus times number of turns times 10 to the minus 8 volts. This will be an added formula and the so-called voltage generated for alternator. Okay, but we are not interested. The voltage we are using at home is not the average voltage. It is actually the so-called effective voltage. So we must have to bring out the relation of average voltage with respect to E. Actually, this E here is the so-called RMS. RMS. This is RMS value. Root means square value or the so-called effective value. The voltage we are using at home is actually the effective voltage. And for sinusoidal flux, the relationship of the effective voltage and the average voltage. We are not using the average voltage, we are using the effective voltage. And actually, the effective voltage is a little bit higher than the average voltage. So, if the average voltage is this one, the effective voltage will be a little bit bigger. Okay? This is the effective. This is the average. Okay? For sinusoidal voltage, there is a formula which gives us the relation of the effective voltage and the average voltage, and it's actually given by this one. Okay? So I place it here for sinusoidal flux, meaning if the flux varies sinusoidally, okay, the distribution factor will be 1.11. Okay? Maybe the next time around, I will try to derive this formula 1.11. So, in here, we just accept it that the distribution factor is 1.11 if the flux that interacts with the conductor is sinusoidal flux. It is 1.11. So going back to this equation here, we will substitute the derived E average. What will come out? The RMS voltage now, or the effective voltage, will be, form factor is actually, this should be distribution factor. Okay? It should be the distribution factor times E average. Right? Like what I said, for sinusoidal, the distribution factor is 1.11, so I will place 1.11 for distribution factor times the value of A average. Am I still on camera? A average is actually the derived formula number 1. 4 flux times N times 10 to the minus A. Right? So if we try to expand this one, that's why there is a factor of 4.44 now. Like in the so-called study of transformer, we got the induced voltage. There is a factor 4.44 on the computation of the induced voltage. It's the same. Actually, it emanates from here. So 1.11 times 4, this will now be 4.44 times frequency times flux times the number of turns times 10 to the minus 8 volts. Okay. This voltage here is the one we are using at home. This is actually RMS. Root means square value or just effective value. We are not using the average voltage, we are using the effective voltage. So from now on, under the study of alternator, the effective generated voltage will be 4.44 times frequency times flux times the total number of turns times 10 to the minus 8 volts. Where small letter f is the frequency in cycles per second or in hertz. It's a family name, the one we are using under the study of AC circuit. Frequency is in hertz. Hertz is a family name. Capital letter N is the number of turns. Total number of turns. If we got a coil, it comprises of many turns. So this capital letter N represents the total number of turns. Okay? So if you try to see it, this N here is directly proportional. This N here is directly proportional to the effective voltage. Meaning to say, the total number of turns is actually many or a large value. We could generate a big voltage. If the flux is big also, we could generate the voltage. So the main factor here is if we could increase or decrease the flux and the total number of turns, and we could generate a desired voltage we would like. That's the sign of alternators already. So capital letter N represents the total number of turns, and angle P, Greek letter angle P, is the flux per pole. The unit of this is actually Maxwell's per second, and E is the effective generated voltage. Okay? So actually, we could manipulate this equation here. If we want a voltage something like 13,200 here, we'll just indicate our frequency. Okay? We'll just indicate our total number of flux. How strong maybe the magnetism is. We could determine how many number of turns, okay, that will be needed to generate that voltage. So this is actually very important. We now know the relation of the generated voltage in terms of frequency, flux, and the total number of turns. But the main thing here is the one, what you call this, holding the value of the generated voltage is the flux and the total number of turns, also the frequency. Of course, if the frequency is 60, okay, we could generate a certain voltage, but the main factor here, flux is the deciding factor, and the total number of turns in the value of the so-called generated effective voltage. Okay, that's it, guys. Okay, so actually we got two formulas in the so-called voltage generated for alternators. For the average generated voltage, it will be 4 flux, okay, of frequency flux times the total number of turns times 10 to the minus 8 volts. Okay, and the second one is effective voltage is equal to this distribution factor times E average, and for sinusoidal this is 1.11. Okay, so after inserting this 1.11, we have derived already the general equation on how to compute for the effective voltage for any alternator, that is 4.44 times frequency times flux times N times 10 to the minus 8 volts. So actually, we could use this equation here in the design of alternator. Okay, maybe you place here 2,000 turns. Okay, you know how strong your flux may be. You will indicate your frequency. Actually, you could compute for the desired voltage. So meaning to say, when you rotate your alternator, you know the specification of this, you are sure that what will come out will be the computed value for the effective voltage. Okay, this is Professor David J. de los Reyes. Good morning from Los Angeles.